In this video, I'm going to show you how to create a simple motor controller with a speed controlling circuit. In my previous video, I showed you how to make a simple circuit that would activate whenever an object was detected within a certain distance of the sensor. We'll set this aside for the moment and move on to the next step in our robot, the locomotion circuit. This robot needs the ability to move forwards and backwards, and turn left or right. The decisions we make in this step will affect how we design both our logic circuit and our chassis. There are two popular designs we could go with. Our first option is the typical RC car drive. You'll have one motor that handles the propulsion, going forwards and backwards, and then you'll have a second motor that will handle the turning left or right. This is also the same sort of drive that you would see on a car. Our second option is a tank drive. In this, instead of having one motor in the back and one motor in the front, you have one motor on the left and one motor on the right. Both of these motors handle going forwards and backwards and turning left and right by changing how much each one is rotating in comparison with each other. For this design, we're going to go with a tank drive because we can create the exact same circuit to drive each motor, and it makes our life much easier. Now that we've decided on a drive type for our robot, we now need a way to control the motors. If I just hook up a battery to a motor, it will spin forever in the direction of the conventional current flow, which is from positive to negative. Well, forever until the battery drains. I can reverse the direction of the motor by reversing the polarity on the leads of the motor, but I want to be able to do this automatically. I would have to manually take the power source out, flip it, and put it back in otherwise. There is an additional problem that we face. In order to rotate, a motor stores energy inside of coils to create a magnetic field. This magnetic field interacts with permanent magnets to push and pull the shaft of the motor, or the rotor. Coils resist changes in current. When you cut power to a motor, it generates a current of its own for a small amount of time as the magnetic field is collapsing. This is a problem because it can send too much current to potentially sensitive components, which could fry them. This is why when you take apart simple toys, you'll quite often see a capacitor or a diode soldered across the leads of the motor. As a side note, this is why you should never connect a motor directly to the pins of an Arduino and many other microcontrollers. There are some microcontrollers where you can do that, but they're built to do that. With an Arduino, you'll pull too much current, and you'll likely fry it when you're cutting power to the motor as well. There is one last thing that we need to keep in consideration, and that's the speed of the motor. If I connect a power source directly to a motor, the motor will spin at a constant speed after it gets up to that speed. The speed will change if I change the voltage to the motor, but otherwise it'll stay constant. I want to be able to adjust the speed of the robot similar to how I'm setting distance threshold from the last video. The directional control of the motors can be accomplished with an H-bridge circuit. This circuit is essentially two nearly identical circuits that are mirror images of each other that will activate or deactivate depending on what you put into the circuit. Another useful benefit of an H-bridge circuit is that you can use low current 5-volt control logic to control motors which are driven at higher voltages and currents. Due to the internals of the circuitry, we also wind up protecting the rest of our circuit from that current that we were talking about earlier. The only thing that this doesn't solve is the problem of controlling the speed of the motor, but we'll worry about that in a minute. For our circuit, we will use the L293D dual H-bridge. It can supply between 4.5 and 36 volts to the motors. It can be used to drive two DC motors or a stepper motor, and it can drive up to 1 amp, which is plenty of current draw for what we need. This IC is probably one of my favorite chips because of how simple it is to use. All we need to do is connect the motor voltage to pin 8, 5 volts to pin 16, ground to pins 4, 5, 12, and 13. Now we can get away with connecting just one of those 4 pins to ground, but they act like a heat sink, so I like to connect all of them. Then we connect pins 1 and 9 to 5 volts, pins 3 and 6 to one of the motors, and pins 11 and 14 to another. This leaves us with pins 2, 7, 10, and 15. These 4 pins control the direction the motors spin. Whatever logic state, high or low, the pin is in, the output pin next to it is the same position. For example, if pin 2 is high, that means there's a positive voltage on pin 3, the motor supply voltage. If pin 2 is low, then pin 3 is grounded. As a result, this also means that the motor turns on whenever the logic levels on the control pins are different. If they are both high or both low, the motor does not turn. I'm going to go ahead and build this first part of the circuit here. I start off by connecting pins 4 and 5 to ground. I could also connect pins 12 and 13 to ground, but I'm not using that side of the chip for this demo. In my final design, they will be connected to ground. It's also important to note that these are the heat sinks, so if my chip starts getting too hot, I want to put some bigger metal piece on there, like an aluminum heat sink, in order to help siphon off that heat. After I connect my grounds, I connect pin 8 to 5 volts. This is the voltage supply to the motors themselves. For this demo, I'm going to use the same power supply to power both the motor and the chip, but I'm not limited to this in the final design. Like I mentioned earlier, I can go between 4.5 and 36 volts on this pin. Whenever pin 2 or 7 are pulled high, the voltage that I put into pin 8 will be on their respective output. After my motor voltage, I connect 5 volts to pin 16 in order to power the chip itself. While pin 8 can accept a wide range of voltages, pin 16 is looking for 5 volts specifically. It doesn't have to be precisely 5 volts, but we want it to be close. This chip is designed to run on 5 volt logic levels, so it views 5 volts as on or high, and ground as off or low. There is some tolerance here that we might go into in a later video, but I don't want to mess with it. Next, I connect pin 1 to 5 volts. This is my enable pin for this motor that I'm demoing. When the enable pin is pulled high, this H-bridge is allowed to function. When it is pulled low, the H-bridge is not allowed to function. To test this chip, we are just going to tie it to 5 volts to get a high signal, but I will demonstrate the functionality of the enable pin a little bit later. Next, I connect wires to pins 2 and 7, which are my inputs into this chip. I wasn't sure where I wanted to connect them on the power rails quite yet, so I left them hanging, but I will take care of that in a minute. Pin 2 controls pin 3, and pin 7 controls pin 6. The output pins will reflect the input pins. What I mean by this is if pin 2 is low, or pulled to ground, pin 3 will also be grounded. If pin 2 is high, or pulled to 5 volts, pin 3 will output the motor voltage that we set earlier on pin 8. Lastly, I connect the leads of the motor to pins 3 and 6. These pins, as you might have guessed, control the motor itself. This motor will not spin very fast because it is geared, first of all, and second of all because I'm only supplying 5 volts to it. But that makes it perfect to demonstrate how this circuit works. I plugged my input pins into the ground rails off to the side in order to have easier access to them. As you can see from this demo, after I connect the power, the motor is not spinning. This is because the inputs are both low or connected to ground. The moment I connect one of them to 5 volts, or pull it high, the motor starts spinning. In this case, pin 2 is low and pin 7 is high. With the way the motor is wired to the circuit, This results in the motor spinning clockwise. If I then plug pin 2 into the 5V rail or pull it high, the motor stops spinning. Again, this is because both inputs are the same, and we need the logic levels to be different in order to get the motor to spin. We need one of those pins to be 5V and the other to be ground or 0V. When I plug pin 7 into ground or pull it low, the motor starts spinning again, but now it is spinning counterclockwise instead of clockwise. This means just using these two pins, we can stop the motor from spinning, we can make it spin clockwise, or we can make it spin counterclockwise. Controlling the rotation of the motor will be very valuable for our robot. Lastly, pin 1 provides us with a more convenient way to stop the motors. If pin 1 is connected to ground or pulled low, the motor will stop spinning, regardless of the logic states of pins 2 and 7. If I connect it back to 5V, the motor starts spinning again in the same direction it was spinning before. Now normally, it would be fine to leave this tied to 5V and control the motor completely with pins 2 and 7, but I want to use this pin. I should mention here that although I'm only controlling one motor in this demo, this chip can control 2 motors at a time. I simply make the appropriate connections on the other side of the chip, and I can control 2 motors at the same time. Another note is that this motor is not the motor that I will be using in my final design. I happen to have this motor laying around, and it was perfect for demo purposes. The reason I'm not using this motor specifically is because the leads are all but destroyed and would be nearly impossible to use correctly outside of the way I'm using them now. Now that we can control the direction of the motor, we have one more problem to solve. We want to control the speed of the motor. With this setup as it is now, we can control the rotation of the motors independently, but they will rotate at a constant speed. If we change the supply voltage for the motors, we can change the speed of the motors, but it will change both of them at the same time. So what if we want to control both motors independently? That is the beauty of the enable pins I was just talking about. The 2 enable pins will allow their respective H bridges to function when they are in a high state, but will turn off the H bridge if they are in a low state. If we rapidly turn the enable pins on and off, we can, in effect, change the speed of the motors of the circuit. Enter the 555 timer. I mentioned this timer briefly in a previous video, but we are going to use it here again. The spec sheet gives some formulas for frequency and duty cycle for the astable configuration of the chip. All we really care about is the duty cycle, the ratio of time on to the total time in a cycle. In order to control the duty cycle of the timer, I will connect a potentiometer to my resistors. This will allow me to fine-tune the resistance in the circuit and thus fine-tune the speed of the motors. I start off by connecting a 100 nanofarad ceramic capacitor between pin 2 and ground. This capacitor sets the frequency of our timing circuit. The smaller the value of the capacitor, the greater the frequency, which means the faster our timer circuit will go. This value might change in our final design, but it works for demonstration purposes. Next, I connect pin 1 to ground and pin 8 to 5 volts. These are the power connections necessary to use this chip. After that, I connect pin 2 to pin 6 and put my 10 kilo-ohm potentiometer on the board. The middle pin of this potentiometer will connect to pin 6 on our timer. Then I put a 2 kilo-ohm resistor from one leg of the potentiometer to pin 7. An additional 330 ohm resistor is put between pin 7 and 5 volt. These two resistors help set our duty cycle. By turning the potentiometer, we change the resistance and therefore the duty cycle. Lastly, the enable pin of the motor controller is connected to pin 3 of the timer, which is our output. It should be mentioned that it is recommended to connect pin 4 of the timer to 5 volts and add a small capacitor between pin 5 and ground if you weren't using those pins already. These are not absolutely necessary to get the timer to function, as you'll see in a moment, but they can help it function quite a bit smoother. So if you're having issues with the timer circuits not working correctly, that might be somewhere you want to start. These resistors and capacitor were chosen because I had them close by as I was making this circuit, so the exact values might change in my final circuit. The spec sheet for the 555 timer gives equations to calculate the duty cycle and frequency based off of the capacitor and resistors that you chose, and these are the values I got. The frequency of the timer is approximately 3 kHz, and the duty cycle will range from about 7.6% at the fastest and 1.4% at the lowest. As you can see from this demo, the speed of this motor is now controllable. It's hard to see how much I am turning the potentiometer, but if I turn it all the way clockwise, the motor doesn't spin anymore. This is because the enable pin isn't on long enough for the current in the motor to build sufficiently to cause it to spin. If the potentiometer is turned all the way counterclockwise, the motor will spin at its fastest with this timer circuit. Thank you for watching this video. Please consider subscribing for more content like this. I always have fun controlling motors, and even more fun using motors to move other stuff around. Let me know in the comments what projects you plan on using these circuits for. I love to see all the stuff the maker community comes up with. Lastly, I'll see you in the next video where I will be designing the logic circuit that will tie together the motor circuit from this video and the sensor circuit from the previous video. Until then, stay safe, have fun, and always look for more things to learn.